Hello everyone and welcome to Live from the Lab. This is the show where we talk about different technologies that Bruker has developed to help scientists discover the world around us. Today's topic is actually a little bit out of this world. We're going to talk about a sample that's not necessarily terrestrial in origin. But the other thing that's really unique about today is that we're going to talk about a whole new class of analyzers. So traditionally we've been talking about techniques that use X-rays, but now we're going to switch gears and talk about electrons. So Bruker actually offers a whole host of different detector technologies that you can bolt onto your electron microscope. The first one that we're going to talk about, which is the topic of today's episode, is EBSD, and we have a cool new innovation called the eWARP. Now to learn more about that innovation, we're going to watch a video, and then we're going to head on over to the table. So let's head on over to the video. All right, here we are in the studio, and I am joined by our expert in these electron detector technologies, Tucker. Thanks for joining.
Yeah, hi, happy to be here.
All right, so now this is kind of a little bit different than our normal episode, but hopefully in the future we'll have you on more often. Mm-hmm. So these technologies now, you don't have to have like a Bruker SEM.
Correct, right? Yeah, and in fact, such a thing doesn't really exist. We have a TEM, Neon, but yeah.
Yeah. So now we are going to do a little bit of an aside here.
Yeah.
I understand you've brought a measurement. So what we're going to do is we're going to start that measurement now so that everybody can see it in real time, and then we'll talk about, dive a little bit more.
That's good.
So if we could queue up that video.
Yeah.
So what are we seeing now?
So right now we're looking at the ESPRIT software. We're looking at a secondary electron image of our sample. The sample that we have here today is a Widmanstätten pattern meteorite. And Widmanstätten, yes.
Okay.
Yeah. I clicked acquire there, so we're getting our first lines of data coming in as we're chatting here.
All right. And so the image that we first saw, that was the electron beam image?
Correct, yeah.
All right. So that'd be like the normal one. Now, we have our software, the ESPRIT software here running. You would normally on your SEM have like other software that comes with the SEM?
Yeah, for whichever microscope it might be.
But that data then transfers right into our software, so you don't have to switch back and forth.
Yeah, that's correct.
All right. So that's pretty cool. Now what we're going to do is we're going to go ahead and take that screen, we're going to minimize it in the corner, but for everybody out there, you can just keep watching. That's a live measurement, so real time, and you can see that speed. So that's one of the things that really differentiates this technology is real speed. But before we go to EBSD, let's just take an aside. Let's go back to these electron detectors.
Yeah.
So you have an SEM. It doesn't have to be the Bruker one. Could come from another vendor. Not going to name them, but there are other vendors. And they would have these holes, these ports.
Yes.
And then you can just buy one of our detectors. What type of tech do we offer to bolt onto these SEMs?
Yeah, so we have EBSD, like the eWARP we're talking about today.
All right, and that is a technology for determining what in a material?
So we're talking about, with EBSD, the diffraction of electrons through our sample surface.
Yep.
So it gives us crystallographic orientation of our sample.
All right, so like XRD, it's EBSD, electron diffraction. It's telling us about the structure. We also offer other technologies, right?
Yeah.
So what other ones do we have?
Our other detectors are, we have EDS, so a couple different geometries. We have standard geometry EDS, and we have as well our flat quad detector, which is a slightly different geometry. It comes in like a backscatter detector and very high solid angle. You can do your measurements very quickly with that detector.
And so EDS, that's energy dispersive spectroscopy?
You got it.
Okay, spectroscopy. So that's going to tell us the elemental makeup.
Indeed, yeah.
All right, so that's kind of like the XRFs that we have, but we can do it in the SEM, so we get the resolution of the SEM.
Yes, and to your point, XRF is something we can also do in the SEM as well. On
really?
The SEM.
Well, you have electron source though. How do
you
you
do
do
have electron
XRF?
source, but we can add our micro XRF source, which is something we produce at Bruker. You attach it to your SEM, and then you are instead of sending in electrons to your sample, you are illuminating the sample with X-rays instead, and using that fluorescence to see what is the elemental composition of the sample.
And that'll give you a sensitivity to other parts of the periodic table.
Indeed, yeah.
Okay.
Yeah, your transition metals and such.
So we have this kind of whole host of different things that people can, buy. They can get those things stuck on to the machine. You can order them at the time when you order the SEM.
Yeah, you can order them when you're buying the SEM or after the fact.
Okay. And then they just bolt on. We got a computer and the software and stuff. We put that there, and we help get everything running.
Yep, that's right.
And somebody like yourself goes out there and...
Yep, I do the training or answer questions.
Sure. Yeah, that's always one of the fun parts. I know when I used to do applications, it was always fun to go places and see all the cool setups and stuff like that.
Yeah.
So it's really interesting. Like I said, that Bruker, so we've kind of expanded from doing the X-ray things to the electron things. So we've been doing this for a while, though. This isn't like brand new or anything, right?
That's right, yeah.
So we've been doing this for years. So let's now dive a little bit into this EBSD.
Sure.
So what's EBSD stand for?
So EBSD is electron backscatter diffraction.
Yeah.
Yeah, and we are diffracting electrons through our sample, the topmost layers of the sample, and using that to determine the orientation of crystals in the sample surface.
All right, so in terms of the geometry then, the electron beam is coming down.
Yeah.
And then we got the sample and you tilt it, or?
Yep, you tilt to about 70 degrees, generally.
Okay. So do you have to have a special like end effector or that on your?
You can use a different stage holder that has a pre-tilt of 70 degrees, or you can tilt your entire stage to 70 degrees, or some combination of the two.
All right, so would this be like a measurement where when you put the sample in, you have to make sure it's all set up for EBSD, or is there the potential, if your microscope is set up right, you could actually do EBSD, EDS without having to remount anything?
You can, yes. Yeah.
Okay.
If the geometry is right, so you want to make sure in that case that your detectors aren't blocking one another, right? But if you've set it up just right, indeed you can do simultaneous EDS and EBSD acquisition.
All right, great. So electron beam comes in, hits sample, and we get cones.
Yes.
Of electron diffraction coming off.
Yeah.
All right. And then the intersection of the cone with the detector gives us a line?
Well, it gives us, I think of it as like a cloud of electrons, right?
Okay.
So there's going to be a point of like highest saturation, right? You want to get that set up such that it is reaching the detector. And from there, that cloud of electrons is going to produce a series of patterns called Kikuchi diffraction patterns.
Okay.
And we can index the zone axes, so wherever those bands are aligning on top of each other, right, to determine what is the orientation of a given crystal in our sample.
Neat. So it's the Kikuchi lines then are those diffraction lines, and like you said, we index, bam, we get orientation.
Yep.
And that information now we're getting, that is, again, structural information. So it's very complementary to what you might get from the EDS.
Indeed.
Which is elemental information. Cool. And you could do the mapping, same area if you wanted. So you could even kind of get multiple pictures and things like that. That's really neat. Now, if we look at that pattern, you can see we're about a third of the way, maybe almost a half of the way done. So pretty quick. How long is this one going to take?
Yeah, so we've been talking for about 5 minutes here.
Yeah.
This entire map, whole thing is going to take about 10 minutes.
Okay, whole 10 minutes. So that's pretty quick. Now,
actually, I would say that's pretty slow.
It's slow? Well,
yeah.
I mean, but I'm used to like EBSD. When I've heard EBSD before, I think hours, if not like, set it up before I go home.
Yeah, yeah. Well,
but you're saying 10 minutes is slow.
Now it is, yeah. So the top speed of this detector is something like 14,000 frames per second, right?
Wow.
We are working at about like less than 10% of that top speed at the moment. So instead of a 10-minute map, we could run as fast as 1-minute maps.
Okay, well, then if you're going to claim that, the viewers out there, they want to know, then why are you doing a 10-minute scan? Why didn't you do a 1-minute scan?
Well, sample preparation is in some ways more of an art form than a science.
Yes.
I did not do an excellent job of preparing this meteorite sample.
Yeah.
So even though I still have a bunch of like scratches and unideal parts of my sample, I'm running slightly slower, at this 10% of our max speed, such that I can still get a very aesthetically pleasing and visually interesting map.
All right. So I mean that's very telling to me, because sometimes you hear people throw out numbers, right? Like, I can scan in a minute. But what we're seeing here is this is a real sample. This is one that a real person prepared, and you have real challenges in the lab, like you said, scratches. I mean, anybody who's done one of these mounts, it's like just polishing that and then trying to get it etched right and doing all that. There's so many issues there.
Yeah.
But you're saying real sample, real conditions, 10 minutes EBSD.
Yep, that's right.
Wow. I mean, that's game changing.
Yeah.
To these tech.
I mean, you could have thrown me a low ball, and I would present you a steel that I map in a minute or whatever. But this is this is a sample from space.
That is cool. So on that note, let's talk a little bit about that sample. So it's right here. It's mounted. So I mean, that's about the size. But I understand we have a picture of it, right? So people can see it a little bit closer.
Indeed.
And it has this very German structure. I don't know.
Yes, yes.
What was that name again?
Widmanstätten. Yeah,
okay, Widmanstätten
is how I would say it. Yeah.
Okay. And when we look at it, I see some features.
Yeah, so we see some large-scale texture here. So, I mean, you saw that. It's probably a number of centimeters wide, that kind of thing.
Yep.
And we can see sort of those cross-hatched patterns that are characteristic of this Widmanstätten pattern. Yes, so we can see that large-scale structure.
Yes.
And when we take a look at our map later on, we can see that some of that large-scale structure or similar patterns to the large scale is also present on the microscale.
All right, so that's the almighty question, right? And we'll be able to kind of check it out and see what's going on in both the elemental and a structural level, right?
Indeed.
All right, so with that, if we check out that screen here on his software, so what are we looking at?
So we are looking at an EDS map of our sample.
Is that just like a really, I don't see any features.
Yeah, I would say it's incredibly boring, actually. This is an iron-nickel meteorite.
Yeah.
So we're seeing iron and we're seeing nickel.
All right. Well, I guess that's the episode of Live from the Lab.
Yep,
we can get really boring.
That's a wrap.
Data. All right. So nickel and iron. That's actually good though, because iron, nickel, that is a very normal composition for meteorites, right? So, so in terms of though uncovering more, I mean, if you did this isn't a bad result.
Yeah.
This is just the result, right?
Yeah.
And when we do it in the software, you can actually see the spectrum and stuff too, right?
Indeed, yes. We have the map here. I'd say the spectrum is kind of more interesting than the map in this case. I mean,
it is in this case.
Yeah, I mean, in this case, yes. We might as well just scan a single point because it's a homogeneous sample. It looks about the same everywhere.
Yep. Yeah, I mean, stay tuned. A future episode, we'll dive more into EDS and look at more interesting samples. But in this case, very homogeneous. And we can see right there. So this is that ESPRIT software. This is the same software we were just looking at,
the
EBSD, right?
Yep.
That's really cool. You got one software. So we got this EDS data. Good result. We see confirm it is iron nickel. That's in line with it being a meteorite. Now I want to switch over to EBSD mode because, and you had taken the map before.
And to get there, it's just one click.
Really?
Yep.
So you don't have to go reload the data and do all this other stuff here?
Oh, well, I preloaded it over here. But it's so probably, in a matter of fact, 3 clicks.
Really?
Yeah.
And now the interface, the top part, that looks similar. So we have all those microscope parameters. You have this kind of workflow. But then the bottom part, that's now transformed to be more EBSD-ish, right? And what are we looking at?
So we are looking at, as you said here, we have our different settings. So we input a name for the sample. We can control the number of pixels that we're going to scan over. We have our EBSD tab here, so I can insert and retract my detector like that. I have my capture setting here, where I can capture this secondary electron image.
Okay, so that is the normal image that you get off of an SEM?
Exactly, yeah.
Okay. And then when you switch it, now we see that's the EBSD image.
That's right, yeah.
So and that's a lot more interesting,
I would say so,
than the composition data.
Yeah, and indeed the secondary electron image too, right? Maybe I saw a little bit of different topography and such before. Right. I could see some different characteristics of the sample surface, but I don't really know what's going on in the sample, right?
Right. I mean, this isn't anything outlandish metallurgically either, because it's very common when you have a rapidly quenched material, you're not going to see a compositional difference. But structurally, it's going to be quite different. Now, what's that image that we see on the right? It has kind of these, I see red lines overlaid, but it has these white streaks, things like that. What's that?
Yeah, so this is our Kikuchi diffraction pattern. And we use this, depending on where those bands are overlapped with each other, where those zone axes are present in the window there. We can use that to determine what is the orientation of the sample.
All right.
Or rather, of crystals in the sample.
And this is where it's a little bit different than that conventional EBSD, because the conventional one that uses a phosphor screen.
That's right, yeah.
And so here, in a conventional one, you would just see a picture of the phosphor screen.
Well, you would get a similar kind of data set, but really the way that we're acquiring the data is so much more of the century, you could say. I mean,
it's like going from an old school cathode ray tube to now
kinda, because previously we would have a phosphor screen, right? And we are shooting electrons through our sample, they're diffracting out. right? And they are impinging upon this phosphor screen detector,
Yeah.
or this, and the screen is going to phosphoresce, so it's going to produce light, right? Photons. And we're literally taking a camera, pointing it at the phosphor screen, and we are taking a video of that pattern as we were scanning pixel by pixel.
And then we would be seeing kind of the frames of the video here.
Yeah, exactly.
But what we're seeing now is that's direct data taken
Yes.
from the sensor.
We are, yeah, this is directly, you're sending electrons in, and it's electrons out that we
So the electron, just kind of like a solar panel, like with light, but now this is with electron. Electron comes in, hits the silicon, creates energy, that's directly detected. And that's what we're seeing here, is this pattern. So it's directly detected, and that's the secret to the speed.
That's right, yes.
Right? That's the key to the speed, and that's also why we can do this now. We couldn't do it 10 years ago, because we have that technology. So that's pretty cool. So what it does is it'll capture these images, and then it identifies the lines, right?
Yep. On a pixel per pixel basis. So as I move across here, we can see that the pattern is updating. And from position A to position B, we can see that that pattern is shifting in a measurable way. And we use that to determine, is it this orientation or is it that orientation?
So the overall confirmation, or the overall structure that tells us that orientation of the crystal is at 101, 110, things like that.
Yeah.
And then that little bit of, as you moved it around subtly, it was like, it's just moving. The pattern moves a little. And that means the crystallites are moving a little bit. Yeah. Okay, so what are we looking at here now?
So here I've switched to an okay view. So this is kind of a model of the orientation of that crystal in the sample surface.
Okay.
Yeah. So if I move over here, different orientation. And here, same over here. And so this is kind of a way of visualize. You can drag this around too. You can visualize what the crystal looks like in the plane of the sample surface.
Yeah. And now we also have a little map you can bring up that shows the inverse pole figure, so we can kind of get an idea how orientation of color.
Yeah. So we're looking at the inverse pole figure here in our view. Okay. If I bring up the key, we can see what those colors actually mean, right? So this is a inverse pole figure Y map, and this is the key for that map.
All right, and for those of you out there, if you're not familiar with this, what these numbers mean, this 001, 111, 101. So when we have a cube, 001 is the faces, right? 101 is the body, is a diagonal of a face, right? Kind of, and then the 111, that's kind of the body diagonal. So those are your major orientations in a cube, right? And so what we mean is, like, if it's blue, it's 111. If it's red, it's 001. If it's green, it's 101, and if you're a mix, then you're kind of somewhere in the middle. All right. So the blue means in this orientation, mostly we're seeing 111 orientation. Now the other thing about texture, right, is that this picture, this slice, this is a certain projection off the surface. Which orientation is this?
This is in the Y direction.
So that would be kind of like if this was the sample that's pointing in the plane in one of the directions?
Yeah. We can also look orthogonal to the plane of the sample surface, and that's the IPFZ map, which I'm showing here.
So that would be the one pointing straight out.
Yes, yeah. And it tends to be, if you've not like rolled a steel, for instance, or set up your sample with some specific texture, the IPFZ tends to be the more intuitive and meaningful measure there.
Okay.
I'm showing you the blue here because I think it looks nice.
Yeah, no, it definitely does look nice. But you can get the different cuts. And so I guess you started talking now about those little things on the bottom. Maybe let's look at some. So the first one is going to be your electron image.
Yes, our microscope image. And I can even overlay that with my inverse pole figure map.
Now the second one tells us about the quality of the result.
Yes, so this is our pattern quality.
Okay.
And this tells us, it's sort of a look into the degree of sample preparation, right? So, and also, whether or not one section of my sample is a crystal, or is it more deformed? Is it not, crystal, and that kind of thing.
Yeah.
So if I was to take my Kikuchi pattern view over here on the right side, and I was to bring the cursor over this lighter section, we can see that we're getting a good Kikuchi diffraction pattern. Yes. If I look down there, it might be kind of hard to see, but we can see N 9 out of 12. That means we're detecting 9 out of 12 bands in this case.
All right. So the software knows if it's right in the modeling, there should be 12 bands, and I can positively identify 9 of these.
Yes.
So saying that's pretty darn good.
Indeed.
Okay.
If I move to this big scratch on my sample here, this dark spot, and I'll try to get pixel perfect there. We can. Oh, maybe I'll pick the spot over here. We can see that this is. We don't really see as many Kikuchi bands in this case.
So good.
We're reading n equals 5 out of 12 here.
Okay.
And this is indication, right, that I'm looking at an area of my sample which is not diffracting, or not a diffracting crystal kind of thing.
Now, in terms of generating this,
Yeah.
so you had generated this beforehand. You'd done this indexing. How manual is this versus how automated it is? So you take the data, and then what do you do? Do you just hit a button and it does it, or what do you have to do?
Pretty automatic. I mean, I had to give it a couple bits of information.
Yep.
So we see here we have a phase included. So I've included this phase. And you need to provide the software with some phase. It can be the wrong one, but that will come at the cost of an accurate calibration, right? Because the detector needs to calibrate its own distance. It needs to know how far away it is from my sample. So you should give it something as close as you can to what you think the sample is made out of.
Yeah.
There are some tricks as well to determine a phase if you don't know. We can use the spot mode, for instance, here, and I could use this to search based off of the experimentally, what bands do I see, and how does that translate into a particular phase? Is it this phase or that phase, based off the closeness of fit?
I mean, in the real world, or in the ideal sense, we'd always know what the sample is, right? The phase or the structure, and then we'd have that file that we could use it here. But like, if you don't know what it is, how do you typically figure out what the phase is?
Yeah, so I would do I do it in 2 steps, right? So first step is I would go to my EDS, right?
Yeah.
I would determine from the elemental composition what is a good starting point. Is my sample primarily iron? Is it primarily nickel? Is it whatever it is, right? In this case, if I run a quick little quantification here, it is over 90% iron, the sample. So for all intents and purposes, mostly iron, a little bit of nickel. If I then bring that in here, right, I could maybe guess that it's ferrite or something similar to that. Or I could go to my spot mode here. I could grab from a particular pixel, and then I could search for iron. Then I could go to my phase ID here, run this, and now I can see that this iron delta, iron alpha is a pretty good fit. If I look here, this ferrite, which I've selected, has 10 out of 12 bands and a low pattern mismatch. So, and if we look at the bands here as well, the blue to the red, they match up pretty closely.
Yeah, they do.
Yeah,
they do. Okay. And that all the phases that you got there, do you get those out of a database?
Yeah, so you can load different databases in. You can even add in your own phases if you wanted to create them.
Oh, cool.
Yeah.
Now, what if my sample had 2 phases?
Yeah, that is something that we deal with pretty regularly. If I had a duplex steel sample, for instance, that's ferrite and austenite.
Okay.
And in that case, I could either preload these, or I could experimentally determine what these phases are, and then I could, even after I've acquired my data set, I could reanalyze with a new phase, and it would match, each pixel to each phase.
Okay, and what would the results look like in that term? Then would we get just another set of images, one set for the one phase, another set for the next phase?
So really, our phase map would be different here. So you would see, if I had like my ferrite was red, and or if my austenite was red and my ferrite was green, we would see red and green on this particular image here in the phase map.
Okay, so that's pretty cool then. So a lot of nice information, and you can see there is so much more you could dig into here. We do only have so much time. Speaking of that, by the way, this being a live episode, if you have any questions right now, go ahead, type those in the side of the screen. We'll answer those questions live in just a minute. We also have some questions, by the way, that came in before, so we'll get to those. If you do have questions, you're watching this later, or you see an episode in the future that you're interested in, send them into live.events@bruker.com. We'll make sure to answer those. So now, in terms of the software, this is still kind of a smaller area. This one, how long did this map take?
It took about 10 minutes.
About 10 minutes. So similar to the live one we were doing.
Actually, in truth, this one is a little slower than the one we show up there. So this is about a 30-minute map.
Okay, 30 minutes.
Yeah.
So, but I mean, the detail in 30 minutes, that's amazing. You can make longer scans, right?
Indeed, we can.
And so I think that you've brought something we can take a look at here.
So if we take a look here, so this was a map that I acquired over the course of about an hour.
Okay.
And we can see a lot more of that large scale, like low magnification structure here.
All right, so this is a bigger map.
Indeed, yeah.
All right. What happens if you use the same size? What if I measured the same area, but I just collected longer?
If you do that, that's going to reduce our zero solutions.
Yeah.
So in this case, right, some of these, I've switched back to the map we were looking at before. And maybe we could resolve this scratch, for instance. Maybe I just needed to run longer, right? And then that could reduce the zero solutions we see there. It also helps to reduce misindexation, for instance.
But really, for a well-prepared sample, we're talking about results on this order. How big is this map overall?
This is, the pixel size
microns?
The pixel size is 80 nanometers. We have a 20 micron scale bar. So yeah, probably about 100 micron.
100 micron by 100 micron?
Yeah.
The one that was an hour?
The hour map, our scale bar is here 100 micron.
Yeah.
So I'd put that at maybe like 500 micron. So like,
wow.
Yeah.
So
half a
half a
millimeter.
millimeter by half a millimeter
Yep.
in an hour, EBSD, every pixel, and what's the pixel size here?
Pixel size is 200 nanometers.
200 nanometers. That's amazing.
Yeah.
This speed. So I mean, I think that's really the story to me is like EBSD becomes very relevant now. Before it was kind of niche. It was like, oh yeah, we could do that. It'll take a little while. But now it's so fast. And you get the feedback, like you said. If I prep the sample, I can see in the quality map, you know what, I need to go back, redo some polishing, come back, do the map again. If you had to do like an overnight scan, that becomes kind of a nightmare. Right? Scenario.
Another advantages of our software too is we have this thing called an Argus image, or now sort of pseudo Argus image.
Okay.
Right? And the benefit there is before I even run a scan, I can take a look at my sample, and I'll switch over here to the software. We can look at this virtual forescatter image, and this tells me, right, if I was to see something like this, that I have regions of very high topography, some scratches here, right?
Okay.
So probably if I saw this, and again, I see this before I even do a scan. I just bring in the detector, right? I know that I probably want to take this out and do a little better job of polishing, right?
So what's Argus?
Yes, off the top of my head, I couldn't tell you exactly what it stands for.
What does it mean?
Yeah, so what it's doing is, if I bring up the key here, that might, in any case.
You had mentioned it's about topography. It gives you better topography or something?
Yes, so it's, what we're seeing here is, there's a particular view I'm looking for, but in any case,
sure.
What it's doing is we are looking at a particular section of the sample. So we are splitting, or of the detector. We are splitting the detector into a red, a green, and a blue channel. So sort of like channel 1, 2, 3. And depending on where each of those electrons are landing at my detector, right, I can determine the topography, or I can get a view into the topography of the sample, as well as crystal orientation very quickly. Right?
Wow. So you're getting so much. You're unlocking so much more.
Yeah.
And I think the thing that really stuck out to me when we were getting ready for this episode was this story. I mean, we looked at it in that EDS image, and it was like very lackluster. And that's not saying EDS is lackluster. You can get some very beautiful images from that technique, and the result we got, which was homogeneity, is a result. That's a very good result. But we didn't know how interesting the material was until we went to eBSD, until we went to the other tool in our toolbox, right? So that's very cool. So I think this stuff is really cool, Tucker, and I really look forward to in the future us learning more about it and showing some of our viewers about this. I think it'll be really cool. So with that, let's head on over to our questions. Let's see what people have thrown out here. So the first one is from Adam. And that question is, what is the advantage of the eWARP over a traditional phosphor screen EBSD detector for a sample like this one?
Yeah. Well, in a word, speed.
Speed.
Right. As we were talking about before a little bit, really that older generation phosphor screen technology is pretty archaic, right? We are taking a camera, pointing it at a phosphorescing screen, and our data set is as fast as our video speed.
Yeah.
Right? In this case, with the direct electron detection technology, right, we are using custom-built, purpose-built silicon for the purpose of doing EBSD analysis, right? Yeah. So, which is why we can get to those speeds of 14,000 or more, frames per second.
Right.
Yeah.
And the reason we can do that is because, we're a large analytical company, right? We can innovate things like this. We can build these solutions, and behind this solution, you also get the trust of a big company like Bruker, right? That people like you are there to help answer questions, and we have a service group to help in case you have issues with that.
Yep.
We've been in the game for a long time, and even in the electron detectors for a long time. So having a partner like that you can trust when you're taking this kind of data.
Yeah, and one that is still innovating.
Right. Yeah, that's right. Because I can tell you this. I mean, if I was sitting there in a metallurgical place, a foundry or making parts in a shop, having access to this would become so indispensable. I can imagine my biggest problem is that I'm going to have so many people coming in just asking for that EBSD map.
Yeah.
So, next question from Brian. Why is direct electron detection EBSD so much faster? So you've said it's faster. You said it's faster. Why? Why is it faster?
So part of it comes down to the electronics, as I was talking about before. Video camera pointed at my phosphor screen, right? But also another matter is the signal efficiency, right? So you can imagine that if I was to read photons, right, with my electron signal as my primary signal, right, there's some loss of efficiency moving each step to step, right, that kind of thing. In this case, we really are reading the effect of the electrons on the sample surface. There are fewer intermediary steps, so we're getting more signal from and less noise as a result of that.
Is there any applications, any sample types, or any areas, research areas, market areas, where you think having that speed advantage can be a real game changer for people?
Well, I mean, wouldn't you like to work 3 times faster in any case?
Well, yeah, I mean, I always would.
Yeah.
And I can see the advantage of saying, like, it's now accessible. We see EDS, right? It is proliferated everywhere, right? I don't think there's probably an SEM in existence without an EDS detector on it. And now EBSD is on the same order of speed. And hopefully with the software, we're at the same level of ease of use. Is there any place where you see that this could really, somebody could go, traditionally I couldn't do EBSD, it took too long, results were too fast, but now that it's so fast, this is going to change?
Yeah, I mean, I think cases where you can't always guarantee a perfect sample preparation, it is helpful. I mean, the better you can do, of course, the better and faster your data set is going to be. But if we're talking about a sample, that would have taken, tens of, hours, up to tens of hours, of hours, that kind of thing. If I can now do that in an hour or less than an hour, right? Then that's going to be super advantageous to me. Now I can definitely do that type of analysis where before maybe it was prohibitively time-consuming, right?
Yeah. What comes to mind is before joining Bruker, I worked in a foundry for a little bit, and we'd always have these like grain size standards, and it was the way you did it is we'd take these things, we'd mount them, right, and then you'd polish it. Oh my gosh, it takes so long, right? And then, you get a scratch, you get a little bevel in it, you can do it more, right? Get it perfect. You etch it, you throw it under an optical microscope. And then, for us, it was game-changing when the optical microscope could start counting grains. But still, if you didn't have good contrast, right, optical contrast, or if the grains started getting too small, sometimes, they want a grain size that's very on that lower end. It was a problem with that optical.
Yeah. You bring me to a great point there.
Yeah.
So this is something that is really kind of special about the eWARP as compared to older generation, EBSD technology. With this new greater signal efficiency, and this is an important point, we're no longer limited to, from the average sample, 15 kV or 20 kV, right? We can go down to 10 kV or lower. And 10 kV is kind of the new normal with this greater signal efficiency, meaning that we're looking at smaller regions of the sample. We have a better spatial resolution, right? So I can really look at smaller regions of my sample. So yeah, you could consider using this for, especially in the if one day there's a TKD application, that kind of thing, you can look at those much smaller areas, and maybe even the semiconductor industry could do something like this.
Yeah, so we've got the small area, and then, like I was saying, in the foundry, you could also do the 0.5 millimeter by 0.5 millimeter, which means we can do our grain size standards on the SEM. And we had an SEM sitting there, so now all I have to do is stick a EBSD on there, press a few buttons, and in a realistic amount of time, which I can then feed back into my process, we can get that data, and very trustworthy. So that's game-changing to me. All right, we still do have a few questions that came in before, but we do have one that came in live from Pumpato. I would like to understand how to perform re-indexing in cases where multiple phases have similar unit cells but differ only in elemental composition. Would this require the use of dictionary indexing? So we can't dig in too much, but maybe a quick answer to that.
Sure, yeah. So if I was re-indexing my sample, I could open up this phase list here, and I could search for some other phase. If we go to the duplex example, for instance, I could add in one of these other iron phases. So I could add in an austenite, for instance, bring that in here. I would click OK, and then I click this reanalyze. I'm not going to do that here because it isn't austenite in the sample. It will look kind of ugly.
Right.
But you would just hit reanalyze, maybe change a couple of different settings here. But yeah, we would click analyze, and from there, the software will go through, and again, pixel by pixel, it will reanalyze such that we are now also looking for that secondary phase which we added in.
Yeah.
And as I talked about before a little bit, if I wasn't sure what is the phase in the first case, I can use my spot mode over here, and I can search the database for this phase or that phase using elemental data that I've acquired before as well.
All right. And if you need more, more clarification on that, Pumpato, you can always send that email in. We can have them flash that email up here. And And we'll direct that question and over to you so you guys can connect directly. Or you can always reach out to, the Bruker normal helplines and stuff. We're always here to help.
Yeah.
All right, Charlotte had asked, are there any other advantages to this detector?
Well, I guess, I'd want to underscore that point about spatial resolution again. It's the signal efficiency of older generation detectors was kind of prohibitive to that 10 kV realm of analysis.
Yeah.
So now that we can analyze on a smaller scale, right? We are getting even closer, right, to tens of nanometers, that kind of thing, analysis. 80 nanometer step size, as I've shown here, is still pretty big. We could go as low as tens of nanometers.
Really?
Yeah, maybe 10 nanometers, right? And for some applications, that's going to be really critical.
Yeah. Yeah, I mean, that's the name of the game these days, is that it's digging deeper, looking closer, we start to uncover where samples aren't homogeneous. And some of those heterogeneous areas are the most interesting and also influence the properties the most of our materials. So Deborah then has asked, how does this texture information differ from what I currently get from my XRD? So yeah, I mean, XRD, we can measure texture too, right?
Yeah.
So I could take this, I could go throw it into the into the old system. Maybe we use one of our fancy micro focuses, or heck, you could either throw this on a D6 phaser, and there we would get a pole figure. So we're not going to get a map. We would just get a pole figure.
Yeah.
And we could tell you what's the relative number of orientations pointing up or to the side and that, but we couldn't get you any mapping.
Yeah. Do you want to see a new tab, John?
I would love to see a new tab, Tucker.
Right.
What do you got here? What do
so
you have
over
to show
here
me?
on my screen, I have, we were looking at pole figures. So before we were looking at inverse pole figures.
Yes.
Now we're looking at the pole figure map, and we can see in these different directions where we have more or less texture. Right?
Why were you hiding this?
It hadn't come up. Yeah.
This is very interesting. So my background, I'm a material scientist. So to me, this is my native language. Inverse pole figures, yeah, I mean, metallurgist side of me, I understand those, but like pole figures, that's my first love when it comes to texture. So this is amazing that you could do it. Now, is this for the whole sample or is this for a pixel?
This is for the whole sample. Yeah.
Okay.
And we could even go in and we could take subsets of this data. So if I was really interested in seeing, there's a region of greater texture here or here, I could take a subset, I could draw it around that, and then I could see, what grains in particular correspond to that texture which I'm seeing.
But for people out there where texture is essential, one that comes to mind for me is people who are making these superconducting tapes, right? You got to have this nickel substrate tape, and it has to have very specific texture so you can have that superconducting current going in the right direction. Texture is absolutely essential. If you have the right texture, it works. If you don't, it's going to be catastrophic. Having the ability where I could do it with XRD, get my answer, take another sample, bam, put it in my SEM, and get confirmation of that texture. Absolutely be essential. So it sounds like maybe we've made ourselves some work here. I think we're gonna have to try doing some XRD and EBSD.
Some kind of comparative thing.
Yeah,
cool.
A crossover event. Maybe that could even be an interesting future episode of Live from the Lab. Is we could bring on our texture expert and for XRD, and then we could run the same sample both ways. So, it's great, I think, when we see a technology like this and it starts to make our minds wander in that creative sense, because we never know where we might get, right? All right. So with that, we've answered all of our questions. Thanks so much for joining us, Tucker.
Oh, it was my pleasure.
Yeah, I really look forward to us doing more of these in the future. Thanks, everybody out there, for joining. I'm sure that you've learned a lot. I know I've learned a lot. I've really piqued my curiosity, my scientific curiosity. So, so until next time, though, make sure to keep your signal high and your background low.